Hello, everyone. In this session, we're going to talk about optimization. This is where we are at the moment. Let's turn on this toolbar. I repeated this several times. When we are developing AI models, we follow these models. We follow these 5 steps in general. First of all, we prepare our data. And we talked about how we divide our data, split our data, train, validation, and test. After we secure our data, we build our models. And in this class, we focus on neural networks, although there are other options we can take, like support vector machines or naive Bayes. Other models are also there. And after that, what we do is we train our models using our trained data. And to train our data, we need to define loss functions. Loss function tells us how well our models are doing at the moment. And loss functions quantify this goodness of our models. And after that, to actually update the model parameters, we need to take gradients of the loss in respect of each parameter. To do so, we need to do something called backpropagation, because we cannot calculate the gradient of a network all the times. But to avoid that, we just split or divide our modules into our computational blocks, and gradients flow through that path. And by using backpropagation, we can reduce the complexity of calculating gradients for each parameter. And after we calculate the gradients to update our model parameters, what we do is actually optimize or update the parameters, the values of parameters using this gradient. And in this session, we're going to talk about how we can optimize our model parameters using this gradient we calculated. We already saw some of these techniques, gradient descent. However, that's just the start of the optimization. There are numerous or various methods better than gradient descent. And after that, we evaluate our models and improve performance by iterating through step 1 to 4. All right, that was a short recap. And today we're going to talk about the motivation of optimization, and we're going to have a look at some of popular optimization algorithms. And other than optimization algorithms, there are other strategies we can employ to improve the performance. And when you develop your AI models, you might run into some errors. And I'm going to show you some debugging tips. And then I'm going to summarize this lecture. First of all, the motivation of the optimization. The reason why we want to talk about optimization techniques is because gradient descent is not enough, because there are many challenges ahead of us. Let's review what gradient descent was. What we did was we first initialize the weights, and after that, we calculate the gradient in respect of each parameter, and then multiply learning rate to this gradient, and then update this weight using this gradient. However, it sounds somewhat simple, but in reality, when we try to move our weight, this is the loss space, and our weights are here. and we want to reach the global minimum. But the thing is, neural network loss function is not convex in general, meaning that we cannot find the global minimum very easily. And there exist multiple local minima, and we will find only one through optimization. And we cannot evaluate all the local minima because there are so many. And another example is we can permute all hidden units in a layer and get the same solution. Therefore, it's impossible to track all the local minima. We just need to choose one through our optimization algorithm. But the good news is, it is known that many local minima in deep neural networks are good ones. I remember I showed you this kind of picture, that this is the loss space of general neural networks, deep neural networks. And although this one is, let's say this one is the global minimum, and other minimas have similar minimum values. So even though we do not reach the global minimum, other minimas are also good ones. That's why we try to deepen our networks. Okay, and there are two issues we need to think about here. The first thing is the learning rate. And the second thing is how we initialize our weight. And we are going to talk about this in more detail in the following slides. Choosing the learning rate too low leads to very slow progress. This is straightforward, intuitive. If you set this learning rate very low, then the amount of update is very low, meaning that it takes much longer time to update our weight. On the other hand, if you choose the learning rate too high, then it might lead to divergence. Let's have a look at this diagram. Let's say our first weight was located here. But if the learning rate was too high, then it will move to the other side here. And then here, W2 and W3, W4, and diverge. However, if we set the learning rate, just a proper learning rate, then it might go through this way. And then we can reach the minimum. Therefore, choosing the proper learning rate is a crucial step for optimization. And there are another issue. Even though we set the learning rate properly, if there are some cliffs like this, then it goes to this direction, and suddenly it doesn't go to this direction, but here, and then here. Because here we need to reduce the amount of learning rate, but we do not have the idea of how this this loss space looks like. Therefore, we don't know how to modulate our learning rate. So if there are some stiff cliffs in the loss functions or loss space, then it could be very challenging. And very high derivatives catapult the parameters W very far off. So it throws the parameters away, catapult. And to avoid this, gradient descent or gradient clipping is a common heuristic to counteract such effect. Gradient clipping means if our gradient, so we want to, let's say G star, set some number like, let's say C, an actual gradient value. And if this gradient value is over larger than C, then we don't take this value, but C. So the maximum value any gradients can have is limited by C when we apply gradient clipping. This is one of most common heuristics to counteract this kind of effect. And we are going to talk about this more often when we discuss RNNs. because in RNNs, gradient overflow or gradient exploding is more common than when we are talking about other types of deep neural networks like, yeah. And there are another challenge like saddle point. Here, the gradient is 0. And we want to find some points where gradient becomes 0, because that means this could be minimum or maximum. However, we usually don't think about maximum because we're talking about gradient descent. And there might be many saddle points in deep learning, but it only becomes problematic if we exactly hit the saddle point. However, the luck we get into this saddle point exactly is very low. So you don't have to worry about this saddle point issues that much. There are many points around here, and you can't exactly settle at this point. And somehow you might settle here, here, or here. Then you can get some gradient and move towards the minimum. And I told you that saddle points are not a big problem. However, the plateau becomes a huge problem because the gradients are all 0 here, and it leads to slow progress or no update at all. And the examples are saturated sigmoid activation function or dead ReLUs. We saw this in previous sessions. In the case of, not this one. This is sigmoid, sigma. In this case, when values are out of certain boundary, then the gradient becomes nearly 0, meaning that there is going to be no update. And in the case of ReLU, here, if you just stop here, then there is no gradient and there is going to be no update. So this is another challenge of optimization. And in this case, we have a cliff or a valley. Then small gradient along the slope of the valley might be very hard to follow because you exactly need to follow this path. And if you make just a small mistake, then you'll just diverge here. I showed you this picture here, diverge. So this could happen for this kind of valley. And you exactly need to follow that path, and that is not highly likely. Okay, that was the motivation of why we study optimization. And optimization has been a very popular research topic for the last a few decades. And there are numerous optimization algorithms. And today we're going to discuss some of the most famous algorithms. And the first one was gradient descent. We saw this in the last session. And let's recap what this was about. What we do is we first evaluate the gradient of the loss in respect of the weight. And then to the weight, we multiply a step size. We sometimes call this step size, but learning rate is more common terminology. And then we update weight. And you can think of learning rate as a scale factor for the gradient. And here, the step is like this. We initialize the weight first and pick a learning rate. And then for all data points, we do forward propagation. So let's say there is a network here, and we pass our data point and then get the output. That's the first step. Here it just says we need to do the backpropagation. However, the thing is, the thing we do before 2.2 backpropagation is we calculate a loss comparing the true y and y hat. And after that, we do backpropagation to calculate the gradient. Anyway, we obtained our gradient, and then using our gradient, we update our parameters. And if validation error decreases, we go to step 2 and repeat this process again and again. However, if our validation loss increases or does not increase at all, then we just stop there, meaning that the training process is over. And here, the problem is, because we are using deep neural networks, the dimension of the model parameters is like 1 million or more. And nowadays, we have large language models and large vision models. And typically, these models have like more than 10 billion or 100 billion parameters. And the dimension is very, very high. And very high dimension means it's hard to deal with those dimensions, high dimensions. And another thing is, here we have, because we are using big data, there are like more than 1 million data points. And for just one update, we need to evaluate the loss for all data points. So this second step takes like million steps because we are dealing with millions of data points. And this becomes extremely expensive to compute and doesn't fit into memory. So we are calculating gradient using, let's say our data set is 1 million and 1 million calculation. And for the second step, we need to do 1 million steps again. And for the third update, we need to calculate gradient using 1 million data points. And this is not tractable and feasible. So what we usually do is stochastic gradient descent. And what is stochastic gradient descent? The full sum here, n, is very expensive when n is large. And usually n is very large because we are using big data. And what we are going to do is we are going to approximate this sum using a mini batch of examples 32, 64, or 128. So in the previous example, we passed all the data points here. Here, to calculate gradient. However, for mini batch gradient descent or stochastic gradient descent, rather than passing 1 million data points to evaluate gradient, we pass only 256 or 128 or 64 or 32 data points. And we just approximate that gradient calculated using only this subset of data points approximates the true gradient calculated using the whole data set. So that is what stochastic gradient descent is about. So we are assuming that the true loss is approximated using the batch. Therefore, rather than using the whole data set, n, we're using a much smaller value, b, here. And this could be interpreted that we are just approximate the data distribution of the whole data set using our batch data set, mini batch. And we call this subset a mini batch. And we are going to choose the maximum b value. We are going to choose b as large as our GPU memory allows. We want to make the batch size as big as possible. And typically, B is much smaller than the whole data. And as you can see here, because we are approximating the whole data set using our small batch, mini batch, smaller batch sizes lead to larger variance in the gradients. That's intuitive. And batches can be, when you are constructing your batch, there are two options. The first option is you choose, let's say our batch size is 16. You choose 16 samples randomly at each point. Or you can partition the data set, meaning that from the first to the 16th data set go to the first iteration, and 17 to 32 goes to the second iteration, and 33 to 48 goes to third iteration. So this is what I mean by partitioning data set and pass the first, second, and third, and etc. to each iteration. However, in this case, in the first case, we just choose 16 samples. We sample 16 data points all the time. Therefore, let's say the first data point can be included in the first iteration, and it could be also included in the second iteration, although the probability will be very low for this occasion or for this situation. And both are okay, but when you try to partition the data set, before you partition your data set, you should shuffle or mix your data set to increase the stochasticity. And here are two terminologies you need to remember. The first terminology is iteration. This iteration means a single gradient update based on a single mini batch. An epoch or epoch means complete pass through the training data set. And this is n divided by b iterations. And stochastic gradient descent here, we initialize our weights, pick learning rate, and this is what is different from this stochastic this gradient descent. Here we didn't choose the size of batch, but in the case of stochastic gradient descent, we choose the size of mini batch. And then we draw a random mini batch or partition our data set into batches. And then for all mini batch elements, it was n rather than b. We for propagation and calculate the loss and do backpropagation and update the parameters using our gradient. And the fifth step is same as before. And this allows for training with limited memory, GPU memory, by splitting data into chunks called batch. And it introduces stochasticity. Batch gradients approximate the true gradient. And you can actually mathematically prove that stochastic gradient descent converges to ground truth gradient descent. This is just for reference, so if you don't understand this part, it's okay. This is like first year calculus class, so I'll just skip this part. There is a theorem that a sequence converges, and you can, if you're interested, you can just have a look at on this theorem. All right. However, the problem of gradient descent was we cannot fit into our GPU memory because the data was so huge. And we solved this problem using stochastic gradient descent by reducing n to the batch size b. However, stochastic gradient descent itself also entails some problems. The first problem is, what if the loss space looks like this? The distribution of W1 is quite different from that of W2. And this is the case when the loss function has high condition number. A condition number means the ratio of largest to smallest singular value of the Hessian matrix. In this case, what happens? The gradient is larger in one direction and smaller in the other, so it jitters like this. However, the faster path would be this one. So rather than moving efficiently, it wastes time, and meaning that it is very slow. It becomes very slow, and we don't want this. We want fast convergence because we want to save some computation and energy and time. So that was the first problem. And the second problem with stochastic gradient descent is the loss function has a local minima or saddle point. But the thing is, these two problems are not just for stochastic gradient descent, but also for other optimization algorithms. In this case, saddle point and local minima both have zero gradient, and gradient descent gets stuck at these points. Because it does not receive any gradient, it doesn't know where to move. And saddle points are much more common in high dimension, but I mentioned that this would not be a problem if you don't exactly settle on saddle points. And the log of doing so is very low. So you don't have to worry about this situation that much. Okay, this is one example. Let's say our function looks like this. Then we can calculate the point where the gradient becomes zero. So we are taking partial derivative here. Then in respect of x, y becomes a constant. So let's remove this, and 2x. What makes 2x 0? When x becomes 0. And derivative in respect of y, here we are considering x as constant. And this becomes minus 2y. And what makes minus 2y 0? When y equals 0. So 0.0 is a saddle point. And this process is just same as when we calculate the minimum points. And another problem is the gradients we're calculating when we're doing stochastic gradient descent come from mini batches, meaning that they could be noisy. Rather than calculating gradient using the whole data set, we are using batch. And batch is just approximating the true gradient, and there could be inevitably noise. All right, to summarize, these are another summary of the problems of gradient descent. Gradient scaled equally across all dimensions. And I showed you a picture of this. And another problem of stochastic gradient descent is it requires conservative learning rate to avoid divergence. Why do we need a conservative learning rate? Because we are using noisy gradient. We need to set conservative learning rate. Otherwise, we could take a big step towards a wrong direction. However, in this case, the updates become very small, meaning that we will just end up slow progress. And finding a good learning rate is difficult. And we are going to talk about how we can choose a good learning rate in more detail in the following slides. And to resolve some issues with stochastic gradient descent, we come up with the idea of momentum. The motivation for SGD with momentum is like this. When we actually run SGD on this loss space, where W1 is much longer and the distribution along the W2 axis is smaller compared to that of W1. In this case, SGD oscillates along W2 axis. And we don't want this action because it goes up and down, and this action is not required. And we want to dampen by averaging over time. And SGD makes slow progress along W1 axis because because this distribution is very large, even though we want to move this much, it is not a big step for W1. And we like to accelerate in this direction. And the idea of momentum is updating weights with exponential moving average of gradients. Let's talk about this in more detail. So what does it mean by updating using momentum? And this is the result of momentum. Momentum is averaging the moving direction over time. So the up and down movements are, these movements get averaged, and these movements will cancel each out. So as you move more and more, you don't see these up and down movements, but only the horizontal action movement. That's what this momentum is doing. And what it actually does is it adds the gradient to the previous gradient, momentum. So we are adding up our movements, and those movements will cancel out some repeated actions like up and down actions. However, the movements towards W1 direction will be accelerated. And we are updating our weight using our momentum. And we are taking beta 1 as 0.9 typically. So the first move and the second move, when this is added using this momentum, we multiply beta 1 here. Then this will become this movement. And we initialize beta M0 as 0 vector. Okay, so at first, it just follows the gradient direction, but gradually it becomes the average or added sum of the gradients up to this point. Okay, another formulation of SGD with momentum. We continue moving in the general direction as the previous iterations. In the case of SGD, we update. Here we're denoting W as X. Here alpha is the learning rate, and this is gradient. However, so the implementation of SGD is like this. Up until the validation loss stops decreasing or increasing, we compute gradient and multiply learning rate to the gradient we calculated and update the weight by subtracting this value. And in the case of stochastic gradient descent with momentum, we store up our momentum using this gradient, and we multiply alpha here. In the previous case, our learning rate is located here, but in this case, our learning rate is here. It doesn't matter. They are talking about the same thing, same concept. You can formulate the same concept in different ways. And we update our weight using our gradient. So here, momentum. Here we are using minus sign here, plus sign here. In the previous slide, we are using minus sign here, plus sign here. So basically, they are representing the same thing, same concept. And we build up velocity as a running mean of gradient. And rho is friction, and typically rho is set as 0.9 or 0.99. And I told you that there are alternative formulations. Like we can put alpha here or here. Both are okay. And I told you that you may see different formulations, but they are all equivalent, give the same sequence of x. And traditionally, momentum is introduced as this, but you could decouple the momentum and learning rate. So you can see this way, beta 1 minus beta 1 here, and update using this moment. In summary, I introduced three formulations of SGD with momentum, and you can choose any of them. It's okay. They are all equivalent. And some of you might have heard of exponential moving average. When you set beta as 0.8, it just follows the ground truth value. However, if you increase the value of beta 1, then it becomes damped. The ground truth value is damped. So you can think of moving average as damping of the behavior of the function. And the moving average effectively dampens the behavior of the function. So here is another example. So when the value is smaller, it just follows the ground truth values. So we set larger beta 1, and the damping, effect of damping becomes larger. All right, we've seen SGD with momentum. What we did was we keep track of the velocity, and we add up the current gradient using the stored or kept track, the velocity we're keeping track of. And the actual step becomes this. So we can think of this as combining gradient at current point with velocity to get step used to update weights. And another momentum we could use is Nesterov momentum. This is, we are looking ahead to the point. So rather than calculating gradient at this point, we are calculating gradient at this point. This is where we are going to, using our velocity. And rather than calculating gradient at this point, we're calculating gradient at this point. And then we mix the gradient at this point with the velocity, and actual step will be like this. And you could think of Nesterov momentum as look-ahead version of just naive or basic momentum. And the equation is like this. So here we use x1, or rather than x1, xt, we are adding this velocity here. So we are calculating gradient at the point where our velocity is pointing at. But implementing this could be very annoying because we need to calculate gradient again or calculate gradient using different points. Therefore, what we are going to do is we are applying change of variables. So we set x tilde as xt plus rho vt. And by rearranging some values, we can we can reformulate the Nesterov momentum as follows. So we are calculating new velocity using the current gradient, and new value becomes x tilde plus new velocity and the difference between current velocity and new velocity. Okay, so when you're implementing Nesterov momentum, we'll use this equation rather than this equation. And when we actually implement our optimization algorithms, you will just realize that this formulation makes much more sense. Okay, SGD with Nesterov momentum is much more damped than that of just basic momentum. And this anticipatory update increases responsiveness and leads to faster dampening, and has significantly increased the performance of RNNs on a variety of tasks. And another optimization algorithm is called AdaGrad. Here, what we do is, after calculating the gradient, we calculate the square of the gradient. And we modify the learning rate using this gradient squared. Why do we do this? And these operations are all element-wise. Why do we do this? We are adding a element-wise scaling of the gradient based on the historical sum. As you can see here, we're just adding up these gradients again and again. And this makes the whole update size for each dimension becomes even. And you can also think of it as per parameter learning rates or adaptive learning rates. If the first, if it updated quite large in one direction, then in this direction, learning rate will become smaller. And if in another direction, if the learning rate, the amount of update was small, then in the next step, the step will be increased. And after a certain amount, the update will be modified like this. And the total, so after all, the updates in all directions will be balanced. That's what this AdaGrad is doing. And what happens with AdaGrad? Progress along steep directions is damped. I showed you this picture. And progress along flat directions is accelerating. That's what this AdaGrad is doing. And what happens to the step size over a long time? Think about it on your own after stopping this video. Okay, let's discuss what happens to the step size over a long time. It decays to 0 because we are adding gradient again and again. And this becomes very large. And in the end, there is going to be no update at all. And RMS-Prop is an improved version of AdaGrad. Rather than just adding up or storing up, building up gradients over time, it decays the previous gradient squared. Because if it goes to another area, then we might need more updates in previous directions that was updated a lot. That's why RMS-Prop introduced decay rate here. So rather than just adding up gradients, it decays previous gradient and then add the new gradient here. That is RMS prop. And motivation for RMS prop is gradient distribution is very uneven along each direction, thus requires conservative learning rate. And in this SGD example, gradients are very large in W2 but small in W1. And the idea of RMS prop is dividing the learning rate by moving average of squared gradients in each direction or in each dimension. By applying this concept, beta 2 is multiplied to the previous gradient stored and 1 minus beta to the squared gradient. And we use this added gradient to divide the current gradient. And all these operations are element-wise. And as you can see here, it becomes much faster and the dampings are strong. In division by running average of squared gradient adjusts per weight step size. Division in W2 direction will be large, division in W1 direction will be small. And this allows for increasing the learning rate compared to vanilla SGD. However, in first iterations, moving average is biased towards 0 because this value is initialized at 0 at first. And because we are taking weighted average, we are biased toward 0 at the first iterations. Okay, so up to this point, we've seen 4 types of optimization algorithms: SGD plus momentum and Nesterov momentum. And another class of optimization algorithms that was AdaGrad and RMS prop. Momentum and Nesterov momentum keep track of the moving directions. And if we are tending to move towards this direction, then it will cancel out like this jiggling behavior. And AdaGrad and RMS prop gives adaptive learning rate for each dimension. So basically, these two ideas are similar, and these two ideas are similar, and they, the first group and second group, have different goals. And what Adam is doing is combining these two ideas. Why don't we do these two things together? Combine these two ideas together. So it keeps track of the momentum and the gradients and combine these two as this. So Adam combines the benefits of momentum and RMS prop. That's very simple. So you can see we have 2 beta values, beta 1 and beta 2. And the thing is, what happens at t equals 1? Because we initialize both momentum and v as 0, both m1 and v1 are strongly biased towards their initial value 0. And we should correct for this bias at the beginning of training. And how do we do this? The solution is quite simple. Rather than using these values, we divide these values using 1 minus beta 1 to the power of t plus 1 and 1 minus beta 2 to the power of t plus 1. And this will generate m hat and v hat and we use these values. And this modification removes the bias from the optimizer. Why is it so? Let's say gradient is abbreviated as GT, and the update equation looks like this. And because M0 is 0, M1 is beta 1 M0 plus 1 minus beta 1 G1. M2 becomes, because this is 0, beta 1 times M1 plus 1 minus beta 1 times G2. And if you put this here, beta 1 minus beta 1 times G1 plus this value. And when you calculate M3, this will become beta 1 square 1 minus beta 1 G1 plus beta 1 minus beta 1 G2 plus 1 minus beta 1 G3. And you can see pattern here. You can see the pattern. And this equation is abbreviating this pattern here. And we want to calculate the expectation over MT. And you can put expectation operator here. And here, we assume that GTs are independent, and we can extract this here, and this will become 1 minus beta 1, and this summation. And from high school math or first year calculus class, you might remember this, that the sum of this series is 1 minus beta 1, 1 minus beta 1, t minus 1, no, t, because we have t values, times beta 1, 0, but this one becomes 1, and can remove these two parts, and it becomes 1 minus beta 1 t. So the expected value is not the true GT, but multiplied by 1 minus beta 1. Therefore, we are dividing these value by 1 minus beta 1 t plus 1, and that will become, when we take every expectation operators on the both sides, then it will become expectation of the gradient we want. Okay, that's mathematical validation of how these operations or modifications can tackle the bias towards 0. And you can also combine Aram with Nesterov momentum. That's also possible, but this is less common in practice. And there exists many variants like SGD with momentum, Nesterov momentum, RMS-Prop, eta grid. And we didn't see these operations, but they are also there. And Aram is most commonly used nowadays. And you can compare each operations, each optimizations. Momentum reduces the damping. However, Nesterov momentum is much more effective than basic momentum. And you can also use RMS-Prop, but you can combine RMS-Prop and momentum, and this becomes much smoother. And up to this point, we have used first order gradient. However, we can use second order gradient to update our parameters. That's also possible. And second order methods are faster as they exploit the second derivative. However, these operations are not applicable to mini batches, as the Hessian estimates are too inaccurate if computed from small batches. And it also requires a lot of computation. And because we are using big data, it's not feasible. Okay, so I'll just show you the difference between the first order optimization and the second order optimization. A first order optimization uses linear approximation. So we calculate the gradient here, and we are approximating this function linearly. We move towards this direction, and therefore the error is quite large. However, when we use second order optimization, we are using quadratic formulas, and the error is smaller. However, second order Taylor expansion requires Hessian, and Hessian is quite hard to calculate. So this is not good for deep learning. Hessian takes O(n) squared elements, and inverting takes n cubed. However, we have tens of hundreds of millions of parameters, and that's not feasible. Okay, let's just skip this part. So let's summarize. The first order and second order optimizations. First order optimizations takes less time to calculate. It takes more time to calculate. However, in the case of convergence, it takes more iterations and less iterations for second order optimizations. And as you can see here, because first order optimizations takes less time, this could cancel out the time required for convergence. However, each step takes much longer time for second order optimizations. And there are some controversies among researchers. Second order optimizations might not be superior to first order optimizations. They might be just equally good, but this is very controversial. Anyway, in practice, ARAM is a good default choice in many cases, and it often works okay even with constant learning rate. And sometimes SGD plus momentum can outperform ARAM, but may require more tuning of learning rate and schedule. And if you can afford to do full batch updates, then you could use second order optimization techniques. Okay, that was about the theory of optimization algorithms. And let's implement what we have discussed. Okay. Optimization algorithms. Basically, how we are going to implement our optimization algorithms are as follows. We are going to separate the implementation of the models and the optimization algorithms by doing this. We are going to implement network using different awesome network, different class, and we can create an instance of an optimizer like SGD or momentum or ARAM like this. And for each iteration, this is going to be a backbone of your optimization code. So you might do some data preprocessing or other jobs required. And we'll just retrieve X and Y batch by calling some get mini batch function. And you just need to design this function on your own. And after that, we calculate the gradients. Network gradient passing X batch and Y batch. After that, we get our parameters. Then we pass our optimizer. Parameters and gradients, and do other jobs here. So as you can see here, the implementation of optimizer is separated from that of network. Okay, that's how we tackle this problem. We are modularizing the implementations. Okay, let's first implement SGD. We first need our initializer. This one takes learning rate. And we're going to save learning rate here. And we need to implement the update method. This one receives the parameters and gradients. It doesn't need to know how these parameters are connected or not, because it will just think about the gradients. And for each key in parameters, and let's assume that these parameters are stored in a dictionary, Python dictionary. And what we are going to do is for each key, self LR learning rate times grades. That's all for stochastic gradient. And let's implement the momentum optimizer. We also need to implement two methods, the initializer. Here we need to receive the learning rate and the amount of momentum we are going to keep track of. And we store these values. And we also need to have V to store our gradients. We also need to define the update method. It basically receives the same thing. And if it is the first time, then we need to initialize momentums. And we're going to initialize this as dictionary. And for key and value in parameters, what we do is initialize this as 0 matrices. And why don't we do this in this method, initialization? Because here we haven't received gradients, so we don't know how it looks like. So we are going to initialize this here. And after that, what we are going to do is update the momentum times stored momentum minus self learning rate times grids. And then although I follow this formulation, you can use different formulations. Okay. All right. The next optimizer we are going to implement is Nesterov optimizer. You need to implement the initializer. We need to receive learning rate, momentum, like this. And this is going to be our first PPP exercise. Implement this update method for Nesterov optimizer. Take some time and implement it on your own, and then see you in the next video.